have returned. It's BOOTHDOG again. That fool, Boothman. He sorely underestimated my abilities. A devotion to mathematics is a pathway to many abilities some might consider to be unnatural. Nevertheless, I'm back, despite his best laid plans. I will be your teacher for who's to say how long. Regardless, everything that has transpired has done so according to my design, and I can't wait to continue your instruction of limits, to continue your review for the AP exam, all without that bumbling fool getting in the way. Let's jump right into today's lesson, taught by none other than yours truly. Good morning. Brief announcements for the day. You have an exit ticket due by midnight tonight, same as it's been the last couple of weeks. And before we jump back into our notes for today, okay, I'm very excited to get to what we're talking about today, but first, I want us to recall something. I want us to go all the way back to Unit 2B, Section 2.6, thinking about asymptotes. Specifically today, I want to discuss vertical asymptotes. So for example, okay, suppose we had a function f of x equals, let's just say x over x plus 1. It's a rational function, okay, which means it has asymptotes. Now we can ask about horizontal and slant asymptotes. That depends on whether the function is top heavy, bottom heavy, equal. But vertical asymptotes work a little differently. And hopefully we remember how we find vertical asymptotes. That was just taking our denominator and setting it equal to 0. So in this case, this function, this graph, would have a vertical asymptote at x equals -1. All right, so we have our asymptote, and if we were to actually graph this out, x equals -1, okay, and then of course, knowing what the horizontal asymptote and the intercepts would be, we'd get a function like this. Now, we defined an asymptote as this value that the function is going to continue to approach, but never actually quite reach. What else do we now know that's defined in a very similar way? Yes, the limit. So an asymptote and a limit are very similar concepts. Now, talking about vertical asymptotes specifically, as this function approaches -1, so the limit as x approaches -1, and we can talk about that from the left side and from the right side, what y value is this function approaching? In other words, what does the limit equal? As we get closer and closer to -1 from either side, starting from the left, let's say, the function keeps growing. And we're going to get closer and closer to this asymptote, but we're never actually going to cross it. We can't, because that would make the entire function undefined. So we're approaching positive infinity from the left. And from the right, this function is going to keep getting closer and closer and closer, but in the negative direction. So it'll keep approaching this line, but it'll never actually quite get there. So from the right of -1, this function approaches negative infinity, right? It's going down versus going up. So how would we express this using our limit notation? Well, we have the limit. I think it's time to retire that marker. We have the limit as x approaches -1 from, let's say, from the left, so that's the little negative in the exponent, of this function f of x equals, from the left, what are we getting closer to? What y value are we approaching? We're going up forever, so we approach positive infinity. From the right, the limit as x approaches -1 from the right of f of x, right, we're approaching negative infinity. So we've talked about how we evaluate limits. Okay, so today I want to start talking about limits that involve infinity. So here we're talking about what happens when a limit equals infinity. Now that's a very tricky statement to make, equals infinity. Does it make sense? Does it really make sense to say that something equals infinity? It's kind of along the same lines as our series that we talked about last unit, those infinite sums. Does it make sense to say that we're adding an infinite number of terms and actually equaling a whole number? Mathematicians would say yes, okay? This conceptually, this is what's happening. So this limit, what we're approaching, is infinite, okay? Or negative infinity. So anytime that we're dealing with a limit that equals positive or negative infinity, as we just saw, that only happens when a function has a vertical asymptote. So that's that first blank right there, vertical asymptote. Okay. How do we determine where a vertical asymptote occurs? Okay. It's the same rule as before. So under here, we would write, we simplify the function, and then we set the denominator equal to 0. Same rule as before, exact same rule, nothing has changed. So let's look at some examples here. Find the vertical asymptotes of each function and describe the function behavior when approaching each asymptote from the left and from the right. Okay, so we'll talk about what that second part means in a second. For now, let's look at f of x equals x minus 2 all over x squared minus 5x plus 6. We do need to simplify this completely first, because if anything cancels in the denominator, it's not a vertical asymptote, it's simply a hole in the function. So let's factor the denominator. Right, so x minus 2 cancels and we're left with 1 over x minus 3. So where does this function have a vertical asymptote? This will occur where x minus 3 equals 0, or when x equals 3. So another way of writing this now, using our limit notation, the limit as x approaches positive 3 of this function is going to be either positive or negative infinity. Now, we would be done, but the second part of this question asks us to describe the function behavior on both sides of the asymptote. In other words, exactly what we did in that example before this. Okay. Are we approaching positive infinity or negative infinity? In other words, is the graph going up or is the graph going down? So let me write that out a little more explicitly. To each side of 3, okay, is f of x going up to positive infinity, or is it going down to negative infinity? Now, in calculus, I'm going to teach you how to do this analytically. In other words, we would plug in values very close to this 3 on both sides to see if we're getting bigger or smaller on each side of this asymptote. Okay, that's tedious. That's not really the point of what I'm trying to do here. So I will allow you to simply graph the function. Remember to use your simplified form. So sketch the graph of the function, either by hand or with a calculator or Desmos or whatever, and look, okay, to either side of that asymptote. Are we going up or are we going down? And checking with our graph, we see that the limit as x approaches 3 from the left of f of x is negative infinity. In other words, this function would be going downward. The limit as x approaches positive 3, or I'm sorry, they're both positive 3 from the right of f of x is positive infinity. Now there's a lot of caveats here. It's not enough to say that these are always going to be different. We could be approaching positive infinity from both sides of the asymptote, or negative infinity. Okay? Sometimes we have more than one asymptote, which means we need to check both sides of each asymptote and break apart the behavior in this way. But this is our answer. And again, all this is saying is that as we approach x equals 3 from the left, this graph is going to approach negative infinity. So as we get closer and closer to 3 from the left, we're going down. And then to the right of 3, as we get closer and closer, we're going up. So that's all this fancy notation is telling us. I want to do part B here, and then we'll be done for the day. This time we have g of x equals 1 over x squared minus 4. There's nothing we can simplify. We could factor this, but nothing cancels. So to find our vertical asymptotes, we set the denominator equal to 0 and solve for x. So x equals 2 and negative 2. So here's one of those cases where we have 2 vertical asymptotes. Now to determine the behavior on both sides, we're just going to graph it and look at what's happening. Okay, so the limit as x approaches, let's start with positive 2. The limit as x approaches positive 2 from the left of g of x. And checking on our graph, we see that that goes to negative infinity. The limit as x approaches positive 2 from the right of g of x approaches positive infinity. Negative infinity. I think I just said positive. Negative infinity for 2 to the left and positive infinity for 2 from the right. And we do the same thing, we look at the other asymptote on this graph. So the limit as x approaches negative 2 from the left of g of x is positive infinity. And the limit as x approaches negative 2 from the right of g of x, this is negative infinity. Okay. And there's our answer. So there's nothing really new here aside from the notation. You knew how to take vertical asymptotes, you knew how to find where they are, okay? And you're just graphing it on a calculator, Desmos, and then looking to see, is it going up? It's positive infinity. Is it going down? It's negative infinity. And then just using the proper notation. Okay. So hopefully that wasn't too bad. Tomorrow, and then we'll practice all of this again on Monday and probably Tuesday a little more. We'll look at what happens as we take the limit as x approaches positive or negative infinity. So what happens not when the limit equals infinity, but what happens as x approaches infinity. Okay. That relates to something else that we've studied in the past. Very excited to get into that with you. Exit ticket due by midnight tonight. You have your 9.1 independent practice that I hope you're working on. Join our Google Meet with any questions. Hopefully you're working on your culminating activity that is due. It's kind of coming up, just a few more weeks. Let me know if you have questions, and I'll see you later. I hope you enjoyed today's lesson taught by myself. Yes, I am your teacher now. Please reach out to me with any questions you might have, and I'll see you tomorrow.